Hi, my name is Nafsul Kondakar, and I'm an electrical and computer engineer and the team lead for the Automated Universal Part Singulator project sponsored by Bosch Rexroth.
I'm Kevin Gilman. I'm an electrical and computer engineering major, and I'm serving as a software lead for this team.
My name is Daniel Mack. I'm a mechanical engineer and the mechanical lead for this team.
Hello, my name is Esmeralda Pimentel Enriquez, and I am one of the mechanical engineers on this team.
Hello, I'm Anthony Phillips, and I'm an optical engineer, and I'm serving as the optical lead for this team.
Hi, I'm Abdullah Idris Al-Bar. I'm a system engineer and the procurement leader for this.
Within the world of automated assembly, engineers are always striving to optimize ways to move parts through assembly lines and feed the ones that pass quality checks. One of the most widely used methods to accomplish this is via vibratory bowl feeders. Bowl feeders excel at inserting a single kind of part quickly and precisely, but their specialized design is their main drawback. If a modification to the part is made or a new part altogether is needed, the entire bowl feeder must be replaced. This leads to larger long-term costs, especially for companies that require adaptability within their product design. The goal for this project is to use a Cartesian robot and a high-resolution camera to design and build a flexible part feeder for automated assembly lines.
Our project is the Automated Universal Part Singulator. The system design mitigates issues that are common in currently used bowl feeder designs, such as part jamming, and it provides a flexible modular structure that allows for easy customization and introduction of new parts to the assembly line. The Automated Universal Part Singulator allows for a variety of parts to be sorted and can be modified through the Control-X software to feed parts to conveyor belts in different locations when operating on the factory floor.
The final system consists of 6 major components: the camera, the Control-X machine controller, the gripper, the Cartesian actuator, and the vibratory table. Using these components, we devised a system block diagram governing the inputs and outputs to the system, as well as all the internal communication between the subsystems. Before designing the system, we identified a set of functional requirements, which were in turn used to identify the system requirements. These requirements are broken down to 4 categories: performance, design, power, and safety.
The smart camera initially came with an 8mm lens, but we wanted to find a better one that would be implemented into our system. So we recognized the working distance we would be operating in, as well as the field of view. The field of view was defined by the vibratory table's dimensions. We also have a couple of system requirements. The first one being identification. The system needed to be able to distinguish between different parts that we'd be locating and sorting. So the camera was trained and programmed to do this and was implemented into the entirety of our system. Our second one was resolution. The second requirement was to verify that the camera was high resolution, and we determined this by using the pixel count that was implemented into the camera, which is 1600 pixels by 1200 pixels. Lastly, we have the camera software. The camera software was very straightforward implementing. All we had to do was place parts underneath the camera and then take a picture and then use the profile pattern function and place a box around each part. We can then use the find pattern function to find each part, which is then communicated to the robot, and of course we use other functions in the camera software to improve how well it located and sorted parts.
The gripper consists of a servo motor, which supplies rotational motion. A pinion gear is attached to the servo and spins with it. 2 rack gears are driven by the pinion gear and can open and close to grab the part. A mounting bracket for attaching a sensor sits under the pinion gear. A crossframe supports all the aforementioned components and includes a mounting point for an Arduino Nano. Lastly, a mounting bracket allows the crossframe to be connected to the Cartesian actuator. We designed the gripper to be 3D printed for rapid prototyping. The first version proved the effectiveness of the 3D printed components and verified that the final version could be fully 3D printed. Later prototypes were used to test different sensors and ways to mount the gripper to the Cartesian actuator. Through this prototyping and testing, we verified 2 primary system requirements for the gripper. The design of the gripper fingers on the end of the rack gear were optimized for picking up a wide variety of parts, and various kinds of high friction material were used to improve the gripper's performance.
The vibratory table is an open-ended subsystem. Its function is to vibrate when the smart camera cannot identify a part that is clear to grab. The major components consist of the mild steel, metal plate bent at a 45-degree angle for ease of access for the gripper, mild steel triangles welded onto the corners, compression springs, and a 24-volt DC vibratory motor. One considerable change is that the washers were tack welded onto the springs instead of being in between the springs. This greatly aided in assembly. custom frame design took into account the X, Y, and Z travel of the Cartesian actuator, its weight, and the height of both the smart camera and the vibratory table. It has gone through a few iterations. As you can see, for example, on the screen, our concept design versus the final frame design. An issue we had was the height of the camera and the position of the vibratory table. The camera's original height would have collided with the Cartesian actuator, but thanks to the flexibility of the extrusion holding the camera, that was resolved by increasing the camera's height. For the position of the vibratory table, it could not be changed due to the restrictions of the y-axis travel of the Cartesian actuator, and so the mounting bracket for the camera was remachined to capture the entire view of the table.
The electrical assembly consists of two independent circuits, a high voltage circuit at 480 volts 30 amps 3-phase and a low voltage circuit at 24 volt DC and variable amperage. We had to design the circuit with all the safety precautions necessary and consulted a professional electrician before designing the circuit as well as after wiring all the components. All hazardous electrical components are housed inside a lockable NEMA enclosure and the wires have thick insulation for protection and shielding.
The software that controls the behavior of our system in operation can be simplified to a state machine. To begin, the system waits for the vibration table to be filled with parts to be sorted. When the user pushes the start button, the system transitions to a part search state where the Control X core will communicate with the camera via OPC UA communication protocol, triggering a camera image. The camera will either respond with part coordinates or a no response, indicating that a part cannot be identified. If no parts are identified, the table will vibrate to disperse parts and trigger another camera image. When part coordinates are sent, the robot moves to the part location, picks it up, and transports it to the sorting tray. This process loops until all parts have been sorted, at which point the table will vibrate 3 consecutive times and finally return to the initial state, waiting for the table to be refilled with parts.
The major expenses for our project were covered by our sponsor, that provided parts totaling $53,100. These parts included a smart function kit, a camera system, and an illuminator. Additionally, we spent funds on purchasing individual parts, with $1,920 spent on the frame, $630 on electrical components, and $175 on the vibe table, and $140 on the gripper, and $1,040 for miscellaneous items. The project began in late August of last year. We started with the design phase, where every component was designed based on the derived system requirements. Then we went straight to fabrication, starting with rapid prototyping for the gripper, manufacturing for the frame, and programming for the camera and controller, and eventually the full system, wiring and assembly. Finally, we took the final month to deploy and test the system and get all components ready for design phase.